Right, so first of all, thank you very much for allowing me to speak at this conference. My name is Phil Gregory. I work with Simon Cornish at Durham University in the UK. And today I'll be talking to you about how we've been engineering robust storage qubits in ultra-cold rubidium cesium molecules. So first of all, why we're interested in ultra-cold pole molecules is that they have certain features which are interesting. Specifically, molecules give you access to rich internal structure because you have access to vibration and rotation degrees of freedom that are not present in your standard ultra-cold atomic systems. Also, in the case of polar molecules like rubidium cesium, you get access to, in our case, an electric dipole moment, so you have long-range dipole-dipole interactions, and the molecules can also couple strongly to electric and microwave fields. Importantly, this dipole moment is available for molecules in the electronic ground state, and so you also have access to long-lived states while these dipole interactions are present. And so these properties led to many proposals for molecules across the fields of precision measurement, quantum simulation, and quantum computation. So now, just to frame the work that I'm going to show you, I want to describe a kind of novel platform for using ultra-cold molecules for quantum computing, and this is based on a proposal from Kang-Kwen Ni at the University of Harvard. So in her proposal, you have a series of molecules confined to an array of optical tweezer traps, and you take a pair of hyperfine states in the rotational ground state, and you can encode quantum information into that pair of hyperfine states, so you can make a qubit. And these states have no transition dipole moment between them, and so they're non-interacting. And so you can think of this as being a storage qubit that you use to store that information between your gate operations. And you carry out those gate operations by bringing a pair of molecules close together, and you project one of those hyperfine states onto a rotationally excited state, and then you activate a resonant dipolar exchange interaction between your molecules. And that can be used to realize, for example, an I-swap gate. One of the strengths of molecules is that you're not just limited to this relatively small number of states. In fact, you can consider, rather than working with qubits, instead working with qdits. The advantage of using kind of many states rather than just a pair of states is that you can expand the Hilbert space that you work in for a fixed number of molecules in your array. So, for example, a 4-level qdit covers the same Hilbert space as two 2-level qubits. Molecules are very well, very suited to qdits because you have many hyperfine states and many rotational states available. In this work, I'm going to show you how we can engineer long coherence times between a pair of hyperfine states in the ground state, so effectively realizing a storage qubit, but interactions between molecules and accessing larger numbers of states is something that we're actively working on. So in our experiments, we choose to use the molecule rubidium cesium. We create a ultra-cold gas of rubidium cesium molecules by associating from a pre-cooled mixture of rubidium and cesium atoms. That association is done by magnetoassociation on an interspecies Feshbach resonance, followed by stimulated Raman adiabatic passage of those molecules to their rotational and vibrational ground state. In the end, we produce around 4,000 molecules at a temperature of 1.5 microkelvin, and we can image those molecules by reversing this association process. And so what we do is we effectively detect atoms that we get from breaking apart the molecules. And because we have to reverse this process, we have a state-sensitive detection method. We only detect molecules that are in the specific hyperfine state that our stirrup addresses. So what I'm going to do is show you how we can prepare measure coherence times between a pair of hyperfine states in rubidium cesium. So this is the hyperfine Zeeman structure of the rotational ground state n equals 0 of rubidium cesium. We have 32 hyperfine states, which comes from the different ways you can combine the rubidium and cesium nuclear spins. And we label these states by MF, which is the total angular momentum projection along the quantization axis. So the sum of the molecule's angular momentum and the nuclear spins for rubidium and cesium. Often you'll see we label these states like this. So it's NMF with subscript K. And that subscript K is just to differentiate between different states that have the same N and MF. In our association, particularly the stirrup, prepares the molecules in one of these two highlighted states. And those states have MF equals +4 or MF equals +5. We do the stirrup at 181 Gauss, so around here, and then we capture the molecules in an optical dipole trap with a wavelength of 1550 nanometers. So we expect to see long coherence times between a pair of hyperfine states, such as these two, because we have, well, effectively the only difference between those states is a difference in nuclear spin. And so in terms of energetics, they're only really different because of nuclear magnetic moments. And so they're relatively small. You can see here, just the Zeeman shifts in general are small, and we have, say, like 1 megahertz energy shifts over hundreds of Gauss change in magnetic field. In addition, our molecules are in an optical dipole trap. We have to worry about polarizabilities, and we expect them to be almost identical for these hyperfine states. Let's take a moment just to highlight that there is another work done measuring coherence times between hyperfine states in molecules. This is with sodium, potassium, a group of Martins Vierlein at MIT, and they measured a coherence time of 0.7 seconds. So in our experiments, we kind of initially set out to just repeat this in rubidium cesium, but we found what we thought was kind of an interesting story. So to measure coherence between a pair of hyperfine states, we do a Ramsey experiment. In this case, we're driving a 2-photon microwave transition between n equals 0, mf equals 5, and this 0-4 state, which is separated by 200 kilohertz. And this 2-photon transition is driven by microwaves that are 40 kilohertz detuned from the rotationally excited states. You can see the Rabi oscillations on that transition here. To do the Ramsey experiment, we do a pair of pi/2 pulses with a free evolution time in the middle. And what we do in our experiments is we vary that free evolution time, and we map out Ramsey fringes, which occur at a frequency equal to the 2-photon detuning of the microwaves. What we also see is that the amplitude of the Ramsey fringes decays much quicker than perhaps we initially expected. So we observed at first a coherence time of 58 milliseconds, which is an order of magnitude shorter than sodium potassium. And so we wanted to ask the question, well, why is the coherence time not longer? And to answer that, we can think about the various fields that are present, and specifically the magnetic field that we have applied to the molecules. So in this figure, this left panel is again just the hyperfine Zeeman structure of rubidium cesium in n equals 0. And this time we've just color-coded states with MF equals 5, 4, and 3 as red, green, and blue. In this right-hand panel, we've plotted the magnetic moments for each of these states, again as a function of magnetic field. And so this is effectively just the gradient of each of these lines. Now, if we look at the two states that we used for this initial Ramsey measurement, which were the two states that we can form stirrup to, we see that there's quite a different magnetic moment between the two. The differential magnetic moment is 1.8 nuclear magnetons. Now, nuclear magnetons I would normally think of as being small, but when you want to get long coherence times, you have to be you have to worry about very small energy variations. And so for 100 millisecond coherence states, our magnetic field would have to be stable to 7 milligauss, which is quite a tall order and something which has clearly not been achieved in our experiments. However, there are many pairs of states that exhibit crossings as a function of magnetic field. And so, for example, we can use this pair of states, which in general are quite close together in magnetic moments, and exhibit a crossing at 154 Gauss where the magnetic moments are matched. And so that's exactly what we do. We choose this pair of states that have a matched magnetic moment, and so we expect them to be insensitive to this magnetic field noise. We again do a Ramsey experiment, this time using 2 1-photon pulses rather than a 1 2-photon pulse, but the outcome is basically the same, that we observe Ramsey fringes at a frequency equal to the 2-photon microwave detuning. Using this more carefully selected pair of states and carefully selected magnetic field, we observe a significant enhancement in the coherence time. So we observe a coherence time of 1.1 seconds, which is much longer than the collisional lifetime for molecules in the optical dipole trap. So what we're looking at in this experiment mostly is collisional loss of molecules from the trap, which is reducing the overall amplitude. And we can see that the remaining molecules actually are relatively coherent, as observed by the fact that the fringes nearly reach 0, even after several hundred milliseconds. We can further test our hypothesis that it was the magnetic field causing issues earlier by carefully tuning the magnetic field away from this crossing point. And we can see that the coherence time that we observe as a function of difference in magnetic moment between the states kind of has the kind of trend we'd expect. So as we increase the differential magnetic moment, the coherence time goes down. We can fit these results with a suitable fit function and extract the magnetic field noise in our experiment, which was 34 milligauss in this instance, and also extract the maximum coherence time that we observe, which is 1.3 seconds. So this is kind of not surprising. We just had to be more careful with the states that we chose. But now we can ask the question is what's limiting this coherence time to 1.3 seconds? And is there anything that we can do about it? And the answer is we can identify the cause and we can do something about it. So what we've found is that this 1.3 second coherence time is due to small differential tensor light shifts in the optical dipole trap. We would normally think of hyperfine states in the rotational ground state as having the same polarizability, and that's mostly because the wave function should be spherically symmetric, and so the polarizability should just come from the isotropic component of the molecular polarizability. However, there are various components of the Hamiltonian that mix different rotational states. The largest contribution in our case comes from the nuclear electric quadrupole interaction and the anisotropic component of the polarizability. Each of these terms is shown kind of graphically here. So this is the electric quadrupole and this is the anisotropic polarizability. And you can kind of see the colored like lines indicate terms in the Hamiltonian that are non-zero. What we see is that for both of these components, there are off-diagonal elements that couple n equals 0 to n equals 2. And so these contributions lead to mixing between rotational states, such that our hyperfine states have a very small admixture of n equals 2 in them. And this leads to a small tensor polarizability in the ground states, which is around 10 to the minus 5 times smaller than we've measured for rotationally excited states directly. We can use our Ramsey sequence to probe these light shifts more directly. So we can look at the frequency of the fringes, which is a measure of the 2-photon detuning, and measure that 2-photon detuning, effectively the energy difference between the states, as a function of the trap intensity. And what we see is that when both optical dipole trap beams are polarized parallel to the magnetic field, we observe a shift on the order of 1 Hertz per kilowatt centimeter squared. And if we change the polarization of our dipole traps such that both beams are polarized perpendicular to the magnetic field, that shift goes in the opposite direction. We can see that more carefully here. So if we fix the intensity and just change the polarization of the trap beams, we get an angular dependence like this. So beta is the angle between the laser polarization and the magnetic field. What we find is an angular dependence which is that of a second order associated Legendre polynomial, which is exactly what we expect for a tensor light shift. This dashed line indicates the value in free space, i.e. without the dipole trap, and essentially is where these two lines cross. And what we find is that this 2-photon detuning equals the free space value when we set the laser polarization to 55 degrees, which is where this goes to 0. We can show that this is a magic angle trap by repeating several experiments at various trap intensities, and we can show that the 2-photon detuning is decoupled from the trap intensity for this laser polarization. So bringing all this together, we can do our Ramsey experiment in a magic angle trap with our carefully selected states and magnetic field, such that we eliminate both the differential tensor light shifts and the sensitivity to magnetic fields. So this is our result. In this case, the top panel, the shaded region, just shows the maxima and minima of the fitted Ramsey fringes. And then each of these panels below shows a zoom in at various times. What we find is that we can follow the Ramsey fringes out all the way to 1.2 seconds, where we stop because the collisional loss of molecules has reduced the number of molecules to an extent that we don't want to go any further. Effectively, the collisions are limiting the interaction time that we have. Our results are basically have no detectable loss of coherence after 1.2 seconds, so they're consistent with kind of an infinite coherence time. But by fitting, we can extract the minimum coherence time that our experiment is consistent with, and that is 6.9 seconds at a 90% confidence level. So this is a significant enhancement of the coherence time by eliminating the tensor polarizability contribution. It's also useful to consider theoretical limits on the coherence time. So given we've characterized both of these terms, noise and magnetic field, we expect will limit to about 2000 seconds. And if our laser polarization was half a degree away from the magic angle, our coherence time would be about 100 seconds. Just as a quick outlook, we're currently looking at extending coherence times to different rotational states, which we're hoping to do by trapping molecules near to a magic wavelength that's been identified at 1146 nanometers. We expect this magic wavelength to be nearly magic for many rotational states, which is good for either qubits or potentially synthetic dimension type experiments. And we've done some initial spectroscopy of this transition. In Durham, we have a couple of new experiments where we are hoping to put molecules into lattices and assemble molecules in optical tweezers. And that leaves me to just thank members of the Irvidium Cesium team and theory collaborators. And if anyone's interested, we have a paper on the archive on this that should appear in Nature Physics, I believe, at the end of the week. Thank you very much for listening, and are there any questions?
Thank you, Philip. I would like to invite any question you might have. Right, here we can see the June's replies to the previous questions.
Mm-hmm.
Is there any question? Okay, great. Thank you very much, Philip, for the great talk.